So just 60 seconds from now, you'll see that clock stop. And at that time, the hydrogen team is going to discuss their plan with the launch director. They're still working on it.
It was a real threat. We had a launch commit criteria. Those are our requirements that we need to satisfy to be able to launch. If we are violating a launch commit criteria, we are not authorized to proceed.
We had some problems during the shuttle years. We solved those problems as well. In this particular case, with the Space Launch System, the Artemis 1 campaign, what you saw with hydrogen leaks was really the first time these two complex machines ever hooked up.
Engineers are asking for a little more time to get back with the launch director on a go-forward plan. We're standing by for that.
It's still all new hardware. So our understanding of the vehicle is there, but we have to be vigilant about building and operating this vehicle because now we have to bring these humans home safe.
Launch control with an update. Launch director Charlie Blackwell-Thompson has called a scrub of the attempt to launch of Artemis 1 and the Space Launch System with the Orion spacecraft.
Thing is, when you're standing on the shoulders of giants, don't try to dance. Don't do that. Just accept the gift you've been given and march on.
Holy moly! What are we gonna do? Fragments of many sizes. Hey, Jimmy. Houston. Right away, Houston. Vector good. Ag soft. Good order. I hear you have good frost.
December 19th. They rode inside a 5,000-degree fireball through the atmosphere of Earth. Stowed in the spacecraft, almost 250 pounds of the moon.
I was very unhappy about the ending of Apollo. I thought it should have continued at least until 20 flights that were originally scheduled. It was cut short, and President Nixon hung it mostly on the Vietnam War. When Eugene Cernan started to climb up the stairs to the lunar module at the end of Apollo 17, he made a small speech. He was expected to, but he emphasized that he expected that we'd be back. The fact that it's taken this long probably would have been very concerning to Gene and everybody else involved in the program. It has taken far too long.
Symbol of mankind that we can live in peace and harmony in the future.
But we have to remember, why did we go to the moon in the first place? When we went to the moon in the first place, it was not because President Kennedy was a space enthusiast.
Not
He had a political problem. He had a Cold War competition between the Soviet Union and the West. And so there was an argument being made that developing countries should think about following the Soviet model. So in that competition, where the US, of course, was second in the Sputnik launch, was second after Yuri Gagarin, President Kennedy had a larger geopolitical and symbolic problem. And therefore, if the US is going to compete in the Cold War environment, it needs to show that it could compete against the Soviet Union in the most highly visible area, which was space. Once that was done in 1969, the Seymour missions ending in 1972, that political problem was gone.
And to implant experimental probes.
The moon's a very valuable resource, and we were leaving it after we'd only just scratched the surface. It was kind of deflating, but I've never been able to understand how you could invest that much in time, energy, talent, and imagination, and suddenly just decide, well, that's enough. We don't need to carry on with what we've accomplished. We had accomplished a great deal. The lunar landings were the equivalent of our pyramids. It was an evolutionary change in humanity. We saw the world a lot differently after Apollo than we did before.
It's all about financial resources and political will. At that time, they had decided that those moon missions that they had budgeted for, that those were the ones that they were willing to expend the effort and the political will for in the Apollo program. And in fact, there were 2 flight sets that didn't fly. We did convert some flight sets into the Apollo-Soyuz program after that. But that would be the choice that they made in the early 1970s and even before that to slow the program down.
We had quite a hiatus in manned flight. They filled in with the Apollo-Soyuz mission and Skylab in between to fill that empty space. The American program has used spare parts and other pieces mercilessly. You take a look at Skylab, which was the hollowed out third stage of the Saturn V rocket, and the front door was a Gemini door. The only thing of really original construction on Skylab was the solar observatory attached to the nose. The rest of it was known technology that came right out of the warehouses. NASA doesn't stand by itself in projects. It has all kinds of people working on what ifs.
As the last Apollo crew worked on the moon, the engineers on Earth prepared for tomorrow's day in space.
I have a model here of the space shuttle. As you see, it resembles a double-wing airplane on top of a propulsion system. System is going to be designed so all of the costly parts are reusable.
There were a lot of concepts being considered for the reusable space plane. I think even von Braun had some thoughts about that. So it did, and as NASA transitioned after Apollo ended, we transitioned into the shuttle and then launching for the first time in '81.
The Soviet Union went in a different direction after the loss of the moon and the Apollo program. They focused on long-duration space stations because they had relatively inexpensive rockets to go to and from the station. The United States wanted to try to lower the cost of launch and to have more reusable vehicles, which led it to build the shuttle. There's a number of things one can talk about the shuttle, and a number of promises that some were achieved and many were not. But it was an effort to make space more routine.
I remember I was in the White House when President Nixon presented the first model of the space shuttle and the way it was going to look. He did a ceremony, and it was clear that the space shuttle that was intended to be the support for the space station, as it eventually came to be, had no job at that time because the space station was a long way off and they were not going to do the two at the same time. Budgetary problems, were immense. And so Nixon simply said, well, find jobs for it to do. And it became a space truck, and it did some marvelous stuff.
was at the beginning of the space shuttle program. And as the shuttles were being built in California and then transported to Florida or to other locations to do testing, they'd be transported on top of the 747. You can't make that flight in one big flight. Oftentimes when configuration, they would land at an airport, stay there overnight, and the public would have the opportunity to come see what the next exciting thing NASA was doing. As a kid, 6 years old, my dad's like, come on, let's go. The 747 was parked on the runway at the Denver airport. We parked outside the fence line, and I distinctly remember walking up to the fence line, barbed wire fence in the high grass, looking across the runway and seeing an orbiter sitting on top of a 747. And I was just hooked from that point on.
The human spaceflight took different avenues. After Apollo, we worked through with the shuttle program, and the shuttle program really captured and flourished in low Earth orbit. And I think that's where NASA was wanting to do the microgravity research. And, you know, from that microgravity research, there are new medicines, there are new spin-offs that have come about that. In addition, we learned how to live and work in space. And that's really key, you know, before you can continue to go longer, let's say, on the lunar surface. So I think we've capitalized, and we definitely know how to live into low Earth orbit. And we're gonna take that and springboard that into longer stays on the moon.
Over those 50 years, we learned how to work together. We learned how to build together. We learned how to explore together. And that's what puts us in a position where we're now ready to explore the moon for longer periods of time and starting to lay down infrastructure so that we can stay there.
The Apollo missions, when we first put men on the surface of the moon, represented, I would say, a hallmark of something that we didn't think was previously possible. So that was the first step to say, yes, we as a species are capable of doing this.
Columbia, this is Houston, AOS, over.
Past that point, the focus, certainly with NASA and with everybody who's been participating in this endeavor, has been to focus on how can we do that with longevity and with safety and with a purpose. And to that effect, the International Space Station, as well as the Space Shuttle, represented multiple decades worth of developing our flight technologies, our human capacities, and a number of other areas of research that are going to enable us to go to the moon and stay for the long term.
Pilot Mike Smith, followed by Mr. Solid, Future in Space. Big smile today.
2 minutes and 55 seconds. External tank liquid oxygen pressurization began, and main engine purging was completed.
4, 3, 2, 1, and liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control program. During the flight, telemetry data gave no indication of problems.
15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
We thought we had it knocked. There was, you know, all we knew was what we needed to know, we thought. And all of a sudden, it all went up in flames. And so we get these lessons the hard way. I've been here to see through all of it, but I was surprised at the human reaction when they saw Challenger and other problems like Apollo 13. People found it hard to believe that NASA could fail in such a spectacular manner. It's a dangerous business.
Every time we've had a major accident, it's usually because schedule pressure was playing some role in that, whether it's Challenger or Columbia or lesser-known robotic and unmanned programs. The schedule pressure on people can be very, very subtle but debilitating. People want to do a good job. They want to succeed. They want to work hard. But sometimes under that pressure, that leads to mistakes, even by the most well-intentioned of people. And so you have to be careful. It's a balance. How do you maintain that sense of urgency and focus without giving into schedule pressure that causes people to make mistakes or cut corners that can result in tragedy?
We saw a couple of times when they got in a hurry what kind of problems it caused. The Apollo 1 fire, for instance. Apollo 13, somebody messed up the design in some of the electronics in the fuel system. If those things are caused by people in too much of a hurry, schedule pressure, yeah, probably. Challenger was a problem in pushing too hard. They should never have launched that day. And they were told they should never have launched that day. And they did it anyway. If they'd have waited a day, probably wouldn't have happened. So that's what happens when you get in a hurry. So if they want to take extra time, it's okay by me. I'll wait.
This is Artemis Launch Control. Launch Director Charlie Blackwell Thompson just called a scrub for the launch attempt today, the second launch attempt. The team now going into the cutoff procedure after being unable to resolve a hydrogen leak.
Crew safety is quintessential, and we have the crew as part of our control boards. We have the chief safety officer is a key part of our program, as well as what we call our chief engineer. And then there's a time to kind of go back and say, okay, let's look more fulsomely at this. How ready are we? How close are we on this? How do we understand our margins? And so all this test campaign is building up data that will help us later determine when we're ready to fly.
Sometimes when people say to me, well, we've been to the moon already, what's so hard? And my response is usually, well, maybe your grandfather went to the moon, but you haven't gone to the moon. What have you done? What have you demonstrated? And the people who know the most about spaceflight will not be telling you that this is easy.
Every mission is dangerous. That's a part of the risk, but NASA has a great process, and our industry and international partners have great processes for analyzing that risk, understanding it, and then making risk-informed decisions. So yes, we've got training, we've got evaluations to do, but we've got this amazing team that we're going to be working with, and when they're ready, and when our training is ready, and when the vehicles are ready, we'll go.
It's really hard to leave Earth's gravity, and the capabilities we've put in place do improve the information that we have, the telemetry, the monitoring of our systems. There are a lot of improvements in capabilities, but actually getting to the moon is just hard. And that's going to be that way for a while until there are significant steps in technological breakthroughs. We've only really been working at this for 60 years, so that's a pretty short time frame from a technology development perspective.
We've always had plans to be able to go back to the moon. There's a constant churn in NASA
about thinking ahead. And there's different areas in NASA that are responsible for human exploration, Earth climate research, space station. And so there's always somebody working or thinking about what can we do in the future. And that happened during Apollo, it happened during the shuttle, it happened during the space station. It just takes sometimes a long time to see the execution and the effort that comes from those projects.
History proves that we have never lost by pressing the limits of our frontier. First, for the coming decade, for the 1990s, space station freedom, our critical next step in all our space endeavors, and next, for the new century, back to the moon, back to the future, and this time, back to stay.
I think we've cataloged 50 different studies on going back. Efforts like the Vision for Space Exploration and the Space Exploration Initiative that were designed to take us back to the moon. And eventually those get the political will drops off because it might be associated with a certain administration or a particular implementation.
Some of those earlier programs in the Space Exploration Initiative, it never really made as much progress to get near hardware. And the Congress looked at the price tag and just opposed it. So it was largely done and defeated within George H.W. Bush administration. The vision for space exploration got farther. In fact, there were several different elements, something called the Crew Exploration Vehicle, which we now see as the Orion capsule. There were different rocket designs, Ares 1, Ares 5, that were developed. There was actually a test flight of Ares 1 in experimental mode. That program was canceled during the Obama administration. There is a heavy lift version called Ares 5, somewhat akin to a Saturn V class vehicle. That program didn't really have any hardware developed during the Bush administration, but it did continue into what we see today as the Space Launch System. So there are elements of the Vision for Space Exploration program, which was called Constellation, that did survive and are still with us today.
The shuttle wasn't able to return to the moon. It just wasn't designed for that mission. It wasn't designed for that kind of reentry. And so subsequent to the shuttle, after that became the workhorse of the U.S. space industry, we looked at derivatives of the space shuttle that would be different. There was a thing called Shuttle C that looked at large cargo capability. That would have been the first machine that might have been capable of sending any measurable amount of mass to the moon. It would have still needed a capsule. You can see the development that started even in the Constellation program. That's the nearest program to the Space Launch System and the Artemis programs.
A lot of the capabilities that we have moving forward were generated out of the start of the Constellation program. And so when it was canceled, a lot of the things, especially related to Orion and our ground systems, so the launch pad, the mobile launcher, all translated directly into the path for Artemis. And so here we were able to just continue to work and evolve as the flight hardware evolved.
NASA's budget's kind of fixed. It's not like a DoD budget that's, covers a lot of different things, but I didn't feel like we were that well supported on the Constellation program. You got a lot of smart people, and a lot of the people that work Constellation are working Artemis now, and we had the talent. It just kind of fizzled towards the end. We had some leadership changes in the U.S. at that point in time, so there was a lot going on there. But I think the Artemis program has quite a bit more support in Congress and on the executive side.
NASA operated the shuttle for many years, and there were efforts to come up with a replacement in the 1990s. NASA chose some very high-risk designs. They didn't produce a lower technical risk evolving design that would look like maybe a shuttle Block 2. They proceeded with a program called X-33, which was a very advanced composite tanks, linear aerospike engines, all kinds of things on it. A very, very advanced piece of technology.
Years of hard work and determined leadership still ahead. This is the craft that can carry America's dreams aloft and launch our nation into a sparkling new century.
I think with the idea that if it didn't work, they could still fly the shuttle. Well, the problem is it didn't work. We were still flying the shuttle, and then you had the accident occur in 2003, and we were done with production lines. We could not build a replacement orbiter if we wanted to. We couldn't keep flying the shuttle because plainly, even after certifying a return to flight, it's still a very dangerous vehicle. There was no way really to cure that. And so the program really needed to come to an end. And therefore, since you had not spent time earlier developing a new replacement, what you had to do is go with what parts and components you had. So shuttle external tanks, shuttle solid rocket boosters, familiar engines. I look at SLS and I see something with a fairly high degree of technical inheritance and traceability back to earlier systems, because we had to go with what we had, not future systems that we might wish we had.
I believe that the architecture we have today, which is rooted in shuttle, is we're taking advantage of the investments that have been made. So Orion and what was Ares 1 and Ares 5 in Constellation, we learned a lot about engineering and put a lot of investment in that engineering. So to use those, the evolution of those in the SLS and Orion directly, those capabilities, is taking advantage of an investment that you've already made. Yes, the SLS core stage has borrowed a lot of the concepts from the space shuttle as well as from Apollo, and for good reason. There are things that you don't want to forget in space flight. And when you have a vehicle that you know can fly successfully and safely, you want to take everything you can from that and lean into next generation spacecraft development so that you don't miss anything in terms of capability and safety for the astronauts.
When you look at the configuration that we have from an SLS perspective, it is significantly different from shuttle. The shuttle orbiter really was the brains of that flight vehicle. So all of the avionics, all of that was managed by the shuttle orbiter. When you look at the way the SLS vehicle is configured, we have avionics for the upper stage. We have a brand new invention utilizing engines from the shuttle program.
The RS-25, or the Space Shuttle main engine, is a very well-performing engine. The history of that says we needed to utilize something. We didn't necessarily need to go to a new engine. The solids are very much consistent, a little more thrust because of the added fifth segment. I think we came up with a very good solution based on where we had been. We took advantage of assets that we already had, such as the Space Shuttle main engines, the solid rocket booster casings, and stuff like that. And I think this really provides a more affordable version of what we're trying to do instead of developing an all-new rocket. And then we evolve that capability when we need it.
There's a lot of things that are new and different with this spacecraft and the launch system. While we're building off the heritage that we had during shuttle, for example, on the solid rocket boosters, we're flying much bigger solid rocket boosters. They have very different chemical propellant in them. So again, everything is building off the heritage we have from before, and it's developing the new and moving us forward.
It's all about escaping the Earth's velocity, right? We have to be at a certain speed to get to orbit. You have to spend a lot of fuel to get to that speed. And depending on the payload mass that you're trying to put on orbit and what fuel is remaining that you need to get to the moon is what really drives the size of these vehicles. This is why the SLS is that big. This is why the Saturn V was that big. This is why the Starship is going to be that big and that powerful, because it really is sending a lot of weight.
All of those things are really driven by physics and the mission that we're flying. Shuttle, totally different because we're going to low Earth orbit and we have basically a spacecraft that's a glider that's going to come back and land either here or out in California. Totally different implementation. The capsule scenario is all based upon the re-entry, direct re-entry back into Earth's atmosphere, utilizing the atmosphere to slow down and then splash down in the Pacific under parachutes. So when you look at that configuration, they look similar, capsule-based configuration. It has everything to do with that mission profile, physics.
This system is very similar from that standpoint of what we had during the Apollo program. And what it means is you have parasitic stages. They ride part of the way up. When they're not being used anymore, they're dropped off and they burn up, re-entering into the atmosphere. There was a conscious decision not to recover the solid rocket boosters the way we did in shuttle. And that conscious decision was payload. If you're recovering the boosters with parachutes or whatever, that's weight that you have to carry on the way up. With reusability comes a lot of expense as well.
The Apollo missions taught us much in terms of what aerospace and vehicles of that nature are capable of withstanding in terms of their performance capabilities, the structural rigidity required to escape Earth's gravity. So you'll see a lot of similarities in between the Apollo framework and the SLS. The fuel sources are different. The Apollo rocket had kerosene fueling the F1 engines, whereas today on the Space Launch System we utilize liquid oxygen and liquid hydrogen. But again, that is the culmination of building blocks from Apollo to the space shuttle to give us the capabilities that this rocket has that previous rockets didn't. So starting from the bottom of the SLS 4-stage, we have the engine section, which is where the 4 RS-25 engines are mounted. And that is by far and away the most complex portion in terms of propulsion systems, avionics systems, electrical controls, everything that we need to communicate with the engines to direct the vehicle where it needs to go on ascent. Just above that, we have the liquid hydrogen tank. That is the largest portion of the rocket by volume. It's 131 feet long, standalone. And that is, of course, the fuel source that we utilize for the RS-25 engines. Just above that is the intertank, which is the forwardmost attachment point for the solid rocket boosters. The 2 solid rocket boosters are solid propellant rockets that we utilize to escape Earth's gravity. So it is structurally the strongest portion of the vehicle. And then above that, we have the liquid oxygen tank, which is the oxidizer. And that is a chemical element that we utilize to help the fuel burn in a specific way. And then just above that is the forward skirt, which is where a lot of the avionics and flight computers are housed. So the forward skirt communicates electronically to the engine section and back to mission control at Johnston Space Center to be able to direct the vehicle during flight.
From a technology standpoint, we have a much more rapid production rate available. We have a lot better machines to do the welding. I mean, our welds can be, near perfect. Like I said, with the additive manufacturing, you can build parts that you never could have built before affordably.
One of the key and critical pieces in really all space hardware systems is how some of our systems are joined. So the friction stir welding capability and technology has been infused to a greater extent in the Artemis and the SLS program than it had in any previous program. And one of the benefits of that
specific fabrication technology is the strength that you maintain in those joint sections and the low likelihood of defects in that process.
The traditional welding technique, you would have two pieces of parent metal, which are joined by a filler material heated to a specific temperature. The friction stir welding process involves the mating of only two parent materials, utilizing a pin tool, which is spun to a very specific RPM and travel speed. And as the tool travels through the two pieces of parent metal, those metals are actually blended into one another, as opposed to being joined using the filler material. The actual rocket itself, in terms of size, is assembled fairly simply, but it's putting everything inside of the vehicle that makes things quite complicated.
Long before a space mission is launched, the parameters of the mission must be calculated with the help of high-speed computers.
Think about what the technology was like back in the 1960s and 70s when we flew Apollo. Think about how much has changed in technology since then. There are things today that we have, capabilities we have. For example, the cell phone that you carry in your pocket has a lot more computing power than the original Apollo computers did. So the technology we have today is very different, and it makes it a very different approach with new materials, new avionics, new electronics, new spacecraft design techniques. All of those are different. So when we're doing these test flights, we're actually testing brand new spacecraft. Now, we build on the heritage from Apollo, but everything that we're doing on the Orion spacecraft, very different.
The computers that were used to launch the Saturn V, you know, like the one that steered the Saturn V itself, like 120 names, was nothing. It was wristwatch. And the computers that took us down to the moon were very small. I was a 93-pound setup built by Bendix, and the first one that took us to the moon couldn't keep up with the trajectory. That's why they overshot on that. On the next flight, they made a pinpoint landing, but that's the way they have commonly done it. Learn from their mistakes and it rolls into the next one.
We're certainly more assisted by technology, and we hope to continue to be able to use as it develops. There's obviously a lot of interest in emerging technologies, artificial intelligence, things of that nature, and who knows what that'll bring for us in the future. But for the time being, it's the people that make these rockets work.
Road out to the pad isn't a divided highway, but two road beds filled with loose rock to help cushion the weight. When the crawler transporter is carrying the Mobile platform with the Saturn rocket, there is a total of 18 million pounds moving along at a top speed of 1 mile an hour.
Since the 60s, there have been a number of studies that have been done on how to get our launch vehicles to the pad. Other countries use different versions. We've looked at barges, wheeled vehicles, rail vehicles, a number of other things, and the crawler, a tracked vehicle, was always the best way to get there. So we did Apollo that way, we did some Skylab missions, we did a lot of shuttle missions, so here we are, still making this old vehicle work. It's a combination of a ship, a piece of mining equipment, and a locomotive. It has all those characteristics. We took ownership of it in 1965. We needed to get rockets from the VAB out to the launch pad, so this is the way we transport them. It's 131 feet long, 114 feet wide, weighs 6.65 million pounds. We are now in the Guinness Book of World Records as the heaviest self-powered vehicle in the world. We'd like to go just straight that way, but there were too many rivers in the way, so they kind of had to divert us and make some turns out there and stuff. So no, it's not straight. It ends up being about 4.3 miles out there. From door of the VAB to the top of the pad is 8 hours. When we're carrying the launch vehicle, we go 0.83 miles an hour. We can go a little faster, but we'll keep it right around that speed. Our speed is determined by the amount of vibration we create, because we don't want to vibrate so much that we shake the launch vehicle and cause it harm. We know if we go that speed, we give the smoothest ride to the launch vehicle. So that is always our goal.
As of right now, there is a red crew, as they are named, a specially trained team of individuals out at the pad making an unplanned change to a replenish valve on the liquid hydrogen side. There are 2 technicians and a safety representative that are right now working inside the mobile launcher.
Sending a red crew into the pad is not a standard operation. We develop the capability, we train our folks, we have all of the rescue personnel, all of the emergency personnel available if we decide to proceed with the red crew. But it is not at all a plan. It's not a standard operation. It is a contingency operation.
It is pretty dangerous. When it comes to the ground system, our launch director makes that call, and she did on this call. Charlie Blackwell Thompson is the one who decided to send the red team out when they had a ground hydrogen leak on that, and she will be the one that ultimately calls any scrub, whether it's due to the machinery of the vehicle or from the pad or otherwise.
Hydrogen is a very small molecule and has been a problematic even in the middle of the shuttle program. In 1990, it was called the Summer of Hydrogen, where we had leaks. After operating the shuttle for 9 years, we still found difficulty getting past leaks. You have large interfaces to the vehicle. We had a number of cases where we had hydrogen leaks, and we needed to learn how to operate the vehicle.
The very thing that makes it hard to contain is the very reason that it's so good performing. It is the lightest and smallest molecule. And so when we accelerate this light molecule, we get very, very good, what we would call ISP, specific impulse. And to the layman, that's fuel economy. And so we take a whole lot less mass. You know, hydrogen was developed as a rocket propellant for the purpose of going to the moon, so that we could do it with one shot.
That's launch business. It doesn't matter if I work shuttle payloads, expendable launch vehicles, or human spaceflight. Everybody's launch business delays. Even if everything's perfect on the rocket, you can't control the weather. I worked Pluto New Horizons, which launched on an Atlas V, which was a tremendously exciting mission. I mean, sent the spacecraft to the outer solar system and was traveling 36,000 miles an hour. And I think it took 4 launch attempts. And I think maybe one was a launch vehicle problem. And then you show up at 3 o'clock in the morning and there's a storm, or there's a ship or a plane out there somewhere that's not supposed to be there. Nothing you can do.
We also had to stand down for a hurricane. We actually stayed at the pad for a hurricane as well.
That happens quite frequently around here. It's Florida. We get hit by hurricanes. We don't like that because we have to roll back. It's not a job we want, but it's a job we've successfully done every time we've needed to. There was one time after we'd taken the vehicle out 2 or 3 times, I was being interviewed, and I jokingly said, "That's it, I'm not bringing it back anymore. It's got to stay at the pad and launch." So I got a little more airtime on that than I wanted to.
We had a hurricane on Thursday, and on the following Tuesday, we launched. And the vehicle stayed out there through the whole thing. Just think about that. Hurricane force winds here at the center on Thursday. Following Tuesday, we launched.
GC, go. Booster, go. Control, go. GNC, go. Prop, go. CDH, go. FIDO, go. FAO, go. MPO, go. ECOM, go.
and go. Go. We'll go for launch.
At this time, I give you a go to resume count and launch Artemis 1.
We purposely build in a hold at T-minus 10 minutes so that we make sure we are absolutely ready, configured to pick up that clock from 10 minutes, because that means we are committed to fly that day.
T-minus 9 minutes and 47 seconds.
Charlie gets that go. We are ready to pick up the clock, and she passes that down to the NASA test director and the ground launch sequencer operator to go ahead and pick up the clock. There's no big red button. The ground launch sequencer operator, GLS for short, along with the onboard vehicle sequencer, ALS, those two computers send every command to the ground systems and the flight systems starting at T-minus 10 minutes. So there's no human interaction for sending necessary commands in that entire 10 minutes. If nothing goes wrong, there are no violations through that entire 10 minutes. We're going to launch 10 minutes later. And for Artemis 1, that's exactly how it played out.
And here we go. Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
The floor was vibrating in this room for that launch. It was massively different than any vehicle that I've seen launch from this space center in my career. Amazing demonstration of power. For us, as soon as the boosters light, our umbilicals separate, our command and control is complete. We can't command the vehicle anymore. That's the handoff point to the flight control team in Houston. And so there's nothing we can do to change anything. That's all done by Houston at that point. But it is still so important to us that we are that commitment to watching and hearing those words of, booster separation and main engine cutoff. We've been waiting a decade to hear those milestones.
It is somewhat a level of relief. You do something for years, and then you finally get an opportunity to see it go through. I was very much impressed. My team does all the flight software as well as the integration of this rocket. And we had a flawless flight as far as software is concerned. You're nervous, right, when you see it go off. It reminded me of laying on the side of the road as a kid in 1969 and watching Apollo 11. So I had some emotions there with seeing that. I felt a certain level of accomplishment that we were able to do the things that we committed to do and deliver our commitment to going back to the moon and going to deep space.
Adventure, exploration, good engineering. It's a challenge. And of course, there's the moon and then Mars. And to some people, that's everything. And those are the people that are attracted to NASA. They're driven people. These people work hard. And when their program's really moving, like as in Apollo, and as we will soon be in Artemis, they're pretty much focused on the thing. You're getting the same phenomenon that we had at the Apollo program in terms of people's intensity and drive. You're getting the same type of thing now.
Every person in here on launch day has gone through a qualification program, has gone through a certification program, has gone through every single launch countdown sim, has had to perform at a high level, and every single person in this room is approved to be in their seat by the launch director. So that's the bar. That's how you get on the launch team, is you perform. You are the best at your job. And the most amazing thing about it is our team is extremely diverse, because the inspiration that NASA and the space program has provided over the last 60 years has provided people from every walk of life, every background, that inspiration to say, I want to be a part of that. And they've had that opportunity, and they are part of this team.
You have earned your place in history. You were part of a first. It doesn't come along very often. Once in a career, maybe. But we are all part of something incredibly special, the first launch of Artemis.
Artemis 1 was an amazing achievement for this team, this launch team, this flight control team, the recovery team, all of the manufacturers that went into, all the way down to the smallest little part, all the way up to the big integrated capabilities coming from European Space Agency, from all of our contractors, Boeing, Lockheed. Just an amazing accomplishment of 10 years of very challenging integration and development, working past the challenges through our wet dress rehearsals and our launch attempts, hurricanes, all kinds of exciting stuff that happened last year. It all started here with this team, and it was, I don't really have great words to say how I was feeling. I was just proud to be a part of it.
We actually have hardware right now through Artemis 7. We're a very hardware-rich program.
The orange is the foam on it. It's an insulated foam.
This is the toilet that the astronauts will use for their 3-week mission.
If his big starship doesn't pass muster here pretty soon, that's going to put a real block in the schedule.
You need a lander.
The size of Starship is around 50 meters tall. The size of the Blue Moon lander is around 16 meters tall.
The suits for the Artemis mission are going to have more mobility than Apollo's.
So as we learn how to live in orbit around the moon, that may be the jump-off point from which we leave to go to Mars.
People will be very fascinated by when we look at technologies such as nuclear thermal propulsion.
It is a question of when and how much money we invest in it.